Hey guys, today I'm going to be going through a couple problems with you that cover all the topics that we've done so far this year with Ms. Resnick in AP Physics. I'm going to be going in depth of the process of how to do some pretty rough problems that we might end up seeing in the AP test in May. Hopefully by the time the test rolls around, we'll have all these videos to help us cram and remember everything that we've done earlier in the year. So, the first problem we're going to be doing together covers the following topics and equations: momentum and the consistency equation for momentum, friction and the equation for friction, dynamics and Newton's second law for acceleration, and kinematics and the equations to solve for velocities. So let's get to it.
A .02 kilogram bullet traveling at a speed of 300 meters per second embeds in a 1.0 kilogram wooden block resting on a horizontal surface. The block slides horizontally 4.0 meters on a surface before stopping. Determine the coefficient of kinetic friction between the block and surface. So, what we do in our physics class is we read the problem 3 times. First, to understand it. Second, to really comprehend what it's saying. And third, to get the information we need to solve the problem. So we're going to read it again together one more time. A .02 kilogram bullet traveling at a speed of 300 meters per second embeds in a 1.0 kilogram wooden block resting on a horizontal surface. The block slides horizontally 4 meters on a surface before stopping. Determine the coefficient of kinetic friction between the block and surface. So, what we're going to do is we're going to take a different colored pen, marker, whatever you use to write this problem, something different, something that'll pop out to you. What we're going to do is circle, underline, whatever you'd like. We're going to make the important information pop out to us, so that's what we focus on. So first we're going to be looking for numbers. So we need the mass of the bullet, we need the mass of the wooden block, and we need the speed of the bullet, and we need the distance traveled by the block, and we need to determine the coefficient of friction between the block and the surface. Now we've highlighted the information that's important to us to solving this problem. Okay, so now that we've read our problem, we've dissected it, and we've taken all the information that we need, we're going to draw a sketch to solve this problem. That's the first thing you always do when going about solving a word problem given to you in physics. So, what I like to do is I was taught to use different colors when drawing my sketches because visually it allows you to understand more how a problem will look in real life because each item will have its own color, so you won't be getting confused as to what is which. So, the problem states that a bullet embeds into a wooden block. So my bullet is going to be blue. And this sketch is going to have different parts of it. It's going to be in 3 different pictures, but the whole sketch is the problem given. So, this is my bullet, and it is traveling this way towards a wooden block, which I choose to be red, that's lying on a horizontal surface. That's the first part of my sketch. The second part of my sketch is when the bullet embeds into the wooden block. And then together, the wooden block and the bullet move 4 meters horizontally. And I'm going to give this picture some direction so we know which way everything's traveling. I'm going to say the bullet initially was traveling horizontally in the positive direction. So for this whole thing, I'm going to put my direction symbols positive, negative for the whole thing, and then up and down. It's really important that you put directions on your sketches so you know which way is positive and which way is negative, so when you actually solve the problem, you can see which it is. So this is our sketch, and this is what we're going to be going off of to draw the next thing, which is our force diagrams. So for the second part of this process to solve this problem, we're going to draw some force diagrams. So for the first part of our sketch, we're going to draw a force diagram for the bullet and one for the wooden block. So they both have a gravitational force pulling down on each object. So this is going to be force earth on bullet, and force earth on wooden block. Now, the bullet does not have an upward force on it since it was shot. So it's only going to have a horizontal force from the gun it was shot from. So force gun on bullet. And the wooden block is resting on a horizontal surface. So it's going to have a normal force of the surface pushing up on the wooden block. And again, we need to give these directions. So we have to label them positive, negative, negative, positive. And again, positive, negative, negative, positive. Since the wooden block is stationary, it's not moving, it's just going to have vertical forces. But since the bullet has a velocity going in the positive direction, it's going to have a force going horizontally in the positive direction. But since it's not on a surface, it's not going to have a normal force pushing up on it. Okay, so it's for the second part of our sketch, we're going to draw two more force diagrams. And they're going to look a little different now because the bullet has now embedded into the wooden block. So we're going to start with the bullet. The bullet now has a gravitational force downwards because it now has embedded the wooden block, and so they also share that force. So this is going to be force earth on bullet. And it's also going to have now that normal force from the wooden block. Normal force wooden block on bullet. And since it has hit the wooden block, it's going to have a friction force in a negative horizontal direction because that's what's slowing down the bullet. So friction force, wooden block on bullet. And we need to label our directions, of course. So for the wooden block, it's still going to have that gravitational force pulling down on it. Force earth on wooden block. And it's also going to have the normal force from the surface. Normal force surface on wooden block. And at this point in our sketch, we have just drawn the bullet and the wooden block as the bullet hit it, not just as the wooden block starts moving. So that will be the next force diagrams that we draw. And we need to label our directions as well. So for the last part of our force diagrams, for the last part of our sketch, the bullet is being slowed down by the wooden block, and the wooden block is now moving in the horizontal positive direction because of the bullet pushing it. So this is going to be force bullet on wooden block, and then it's also going to have the gravitational force from before that didn't change, and the surface force, the normal force from the surface. So these are our final force diagrams for this problem. Now on to the fun part, the math. So here I've drawn all the givens that we highlighted in the problem when we first started. They gave us the mass of the bullet, the mass of the wooden block, the velocity of the bullet, the velocity of the block, and this is at the beginning, so this is their initial velocities. And they state that they end at rest, so we can assume that their final velocities are both 0. And they tell us the distance the block moved is 4 meters, so our delta x is 4 meters. So, what we plan to do with this problem is we plan to use the kinematics equations of velocity, the one that looks like this. We plan to use this to find our final answer, the coefficient for kinetic friction. So, this is our goal. This is what we want to use. So, in order to do that, we first need to solve for the velocity. And to do that, we're going to use the momentum consistency equation. What the momentum consistency equation is initial. We're going to use the letter for momentum, which is P. So initial P equals final P, or momentum. And what this equation looks like is this. This is why we have these labels here, M1 and M2, so we can differentiate between mass 1 and mass 2. It's mass of bullet and mass of wooden block. So, we're just going to plug the numbers we're given into this equation. So we are given, I'm also going to continue using the color coordination so that it's easier to follow. Now, as you see, this is multiplied by 0. So momentum for the second item, the wooden block, is going to be canceled out. So when we continue on with our equation, we don't have to worry about that part. And this multiplied together is 6 kilograms meters per second. And these labels do combine. Now we just divide to solve for V. So now we're dividing by kilograms, so these cancel. And V, this is our VI, our V initial, equals 5.88 meters per second. So the next thing we have to solve is the friction force of the wooden block on the bullet. And the reason we're solving for this is because we need to use Newton's second law equation to find acceleration, because for our end equation from kinematics that includes acceleration. And the reason we're solving for the friction force is because our force diagrams before proved that the normal force and the gravitational force cancel out. And so the only force we are left with is the friction force. So, in Newton's second law, when it states the sum of the forces, it's only going to be our friction force because the other forces are canceling. But that will be in the next step. First, we need to solve for this. So, the friction equation states that sum of the forces equals mu times normal force. And we can say that normal force is mass times gravitational force. That is just understood. And when we plug in for mass, we're going to plug in the mass of the bullet and the wooden block because the friction force is between the two. So, we're going to plug in the information that we are given from the problem. And then our gravitational force is 9.8. And then when we solve for this, this is going to be Newton's. So our sum of the forces is going to equal, this is negative because it's pulling down, so it's going to be negative 9.996 mu kilograms. We always have to include both labels. Now we can plug this into Newton's second law equation. So Newton's second law consists of acceleration equaling the sum of the forces, which we just found, divided by the mass. And again, when we do mass, we're going to include both the wooden block and the bullet because the friction was between the two. So, we're going to use the quantity we found before for the sum of the forces. These labels are going to cancel, so it's just going to be mu. And acceleration equals negative 9.81 mu. Now we have all the quantities we need to solve for the coefficient of kinetic friction between the block and the surface. We're going to use the kinetic friction that we mentioned at the beginning of this video.
V final squared equals V initial squared plus 2a delta x.
We solved for all the values, and now we need to plug them in. So the final velocity was 0 meters per second because both systems had come to a complete stop. And we determined that the initial velocity was 5.88 meters per second, and we must square the whole thing. And the acceleration was negative 9.81 mu times 4.0 meters. Okay, now we just have to solve for this. So this is just going to be and then we're going to move this to this side so we could set them equal to each other. So this become a positive 78.48 mu times meters equals 34.57 meters squared seconds squared. Now we just divide to get mu alone, so we're going to divide by 78.48 meters So mu is going to equal 0.44. And this is our answer. This is the coefficient for kinetic friction between the block and the surface. And that's our first problem. So the next problem we're going to be doing together is a problem you might see in the multiple choice part of the AP test in May. So we're going to read this together. You were doing squats on a bathroom scale. You decided to push off the scale and jump up. Estimate the reading as you push off and as you land. Now don't let this problem scare you because there are no numbers in it. Sometimes you don't need numbers in a physics equation to give a solution. There might only be an explanation with words. Don't let that intimidate you. This is Newton's third law. Force 1 on 2 equals negative force 2 on 1. This is the reason why you can stand and not fall through the floor or be lifted off the ground. Because your gravitational force and your normal force balance. And that's why you could stand. So, in this problem, by Newton's third law, the bathroom scale reading is equal to the actual weight of the person. So when you stand still on the scale, it reads your real mass. And when you jump, there's an extra downward force exerted. So this means there's an additional extra normal force pushing up, giving more apparent weight. And it's the same case when you land. When you land, it's going to have a force that is equivalent to the opposite force. And that is how you can explain the answer to this equation. So when solving this, if this is a multiple choice question on the AP test, you just look for the answer that states that when you are pushing against something, Newton's third law states that there is an equal force in the negative direction of that force that is being pushed, that you're standing, no matter what the case. That is what this law means. Just if this ever comes up, just think of you standing. The gravitational force that is pulling down on you has an equal force in the opposite direction, in the positive direction by the normal force that the surface is pushing on you. Our next and final problem for this video is going to cover the topics of momentum in impulse and in collisions. This problem reads, a 1,340 kilogram car traveling east at 13.6 meters per second has a head-on collision with a 1,930 kilogram car traveling west at 20.5 meters per second. If the collision time is 0.10 seconds, what is the force needed to restrain a 68 kilogram person in the smaller car? Draw a momentum bar graph to show the smaller car's impulse. So, what's important here? We're going to take our different colored marker, the mass of the smaller car and its velocity or speed, and the larger car and its velocity. The collision time is very important. Their directions show positive and negative directions by the sense that one is going east and one is going west, so you can assume that they're going in opposite directions. The weight of the person, the mass that must be restrained that we're solving for is also important. And we need to draw a bar graph. We can't forget that. So, on to our sketch. For this sketch, we're going to have two different colors again. This could be car 1, car 2. So, the problem stated, car 1, the smaller car, was moving in the east direction, and I'm going to make that the positive horizontal direction. And it was going at a speed of 13.6 meters per second. Car 2 was traveling west, which is going to be my negative horizontal direction. And it was traveling at a speed of 20.5 meters per second. So this is our sketch. This is what's going to help us go and do our math now. We don't have to draw any force diagrams because later in this problem we are going to make a momentum bar graph, which takes the place of a force diagram for this problem, because a force diagram will not apply to helping us solve this particular problem. Here I've written out all the givens that we've taken from the word problem that we've highlighted before. Now, we're going to start off with the momentum consistency equation to begin solving for this problem. And again, just as a reminder, and again I've labeled here which car is M1 and M2. So now we just have to plug in our givens into this equation. We get this label because these two cancel, and now we have solved for the velocity. And now we are going to plug this in to an equation to find force using momentum. Taking a look at our equation sheet that we are going to have on the AP test, that is where we are going to find all of the useful equations that we are going to use to solve our problems. So, we have our time, and now we have our velocity, which we can plug in to get our momentum value. So, with the equation right there, J equals force delta T equals delta P, that is what we are going to use to solve the rest of this problem. And this is a lowercase p. Momentum is always a lowercase p. And we want to rearrange this so that we have the force on its own. So force is alone. You always rearrange your equations before you plug any actual numbers into them. That is the most important rule of all. So we have delta P. What is delta P? Delta P equals mass times velocity. So we can plug that into here also. We haven't done any numbers yet, but this will make it so much easier in the end when we get the numbers. So this is our equation we're going to be using. This is what we're going to plug numbers into now. So F equals, we're going to rewrite our equation. And you don't want to confuse the AP test grader, so you always want to write your equations that you're using. And now we just plug in the numbers that we found before. Now this is the mass of the person, since we're finding the force that has to restrain the person. That's why we're not using the mass of the cars. But we are going to use both the velocity that we just solved, and we're going to use the velocity of the small car because we're looking for what force restrains the person in the small car. Is going to equal 13,688.4 newtons. And that is because this label comes from the kilograms times meters per second times second. So it's kilograms meters per second squared, which equals newtons. So this is the answer to the first part of our problem. Now the second part, we have to draw our bar graph, which, like I said before, is in place of our force diagrams. To draw a bar diagram for momentum, it looks like this. There's an equation that you use, P initial times delta P, or impulse, equals P final. Now we just have to solve for these to draw a bar chart. So P initial equals mass times velocity, and this is going to be for the small car, this bar chart. So we're going to plug in for the small car. When you get these values, you can just label them on your chart for accuracy so that the grader knows where your numbers are coming from and where your bars are coming from. And it's simple. And you just do that for all of them. And the impulse is simply the final momentum minus the initial. And if you want to double check your work, just remember initial momentum always equals final momentum. This cancels out to equal that. You can check with your calculator, and we're good to go. Okay, that's all I got for you guys today. Thank you so much for watching. I hope this video was helpful. I hope this really explained how to solve some problems and gave you some helpful tips on how to solve problems in the future if you ever get stuck. And I'll see you guys in class.